Are you a parent, caregiver, or just so happen to find yourself in charge of babies frequently? Tired of the constant worry and need to check up on them while they're asleep just to make sure they're still okay? Well, we're here to help you. InfaCam has been designed specifically with you and your baby in mind. This all-in-one baby monitoring device provides you with a non-intrusive solution that can monitor your sleeping baby's well-being so that you don't have to. On average in the United States, about 35 babies out of 100,000 live births do not survive due to unexpected causes, referred to as sudden unexpected infant deaths. And with your help, we're here to combat this. In order to provide you with the most peace of mind, we will monitor the body temperature, heart rate, and breathing rate of your baby to ensure that they are still healthy in the most ways possible, and will alert you the moment anything falls out of line.
InfaCam is made up of three main pieces of hardware. A stethoscope and microphone composing an acoustic amplifier is connected to a Raspberry Pi and is buried inside of a foam pad. The Raspberry Pi is also responsible for powering and controlling our infrared thermal camera. Our current investment for the proof of concept is approximately $600. The goal for the production model is to cost less than or be equal to our prototype. I was responsible for integrating the hardware and providing real-time, reliable data to the data analysis team. This screen shows a stream of audio data acquired from my heartbeat in real time. Every several frames a heartbeat can be seen. The bottom of the screen shows 3 examples of what a low gain heartbeat looks like. This is me testing the thermal camera. It is clear that when I exhale, there is a significant change in temperature based on the change in color of the region under my nose.
Hi, I'm Martin. My responsibility is temperature analyzing. I need to collect information from the region of interest, including forehead and nose area, convert the value from ROI into temperature, and then send them to analyze function. Here is my first version of my code. It will basically read the scale and the ROI area from a thermal image, and then convert RGB value of pixel in ROI into temperature based on scale, and then it will return the average temperature after ROI. Here is my second version. First, we change RGB value into grayscale value so it can consume less computation power. And in this version, we are having a multi-threading. One thread is for reading grayscale value and then converting. Another thread is to monitoring keyboard activity, so user can use keyboard to terminate the monitoring process. I also need to manually get ROI function and analyze function.
After gathering the average temperature value for the ROI over a time window period, the information is passed on to an analytic function to obtain the respiratory rate for the monitoring target. This function will find the best fitted sinusoid curve for the collected raw data, and the respiratory rate will be calculated based on the conversion of the horizontal expansion coefficient of the sinusoid curves, which basically is the period of one breath. And here is the demonstration of how the analytic function will be applied on one window period. As you can see, the scattered dotted plot is the average temperature value for each frame ROI, and the blue line and orange line plots are respectively the best fitted sine and cosine function for the time window. The calculated respiratory rate for each curve is presented in the output of the terminal.
First, we started analyzing the heart rate data using MATLAB. To get the heart sound, we used the stethoscope along with an adapter for our phone to get any recordings. For the analysis, we filtered the raw data using a bandpass filter between 20 and 200 Hz, since that is the frequency content of the heart, and the built-in envelope function to detect the heartbeat, which is shown with the orange curve. Using the analysis along with the 10-second data, we got a heart rate of 78 beats per minute.
This is what the signal looks like. So right now, it's at rest, and if I speak up, you can notice hello. Okay guys, now what I'm gonna do is I'm gonna show 3 graphs. First graph is gonna have 2 lines stacked on each other just to verify so that the data is actually getting filtered. Second graph will show us the frequency of the input data. Third graph will show me the filtered data, which is stacked on graph number 1. Let's take a look. Let's play first online tone generator, and on my VM I'm gonna run the code. Let's see, what does it look like.
I recorded 10 seconds of the heart stream data when the stethoscope was placed on the chest to debug if our algorithm was working correctly. For our algorithm, we used a bandpass filter along with a fine pitch algorithm to be able to determine the heartbeat. In this case, the output of our algorithm was 60 beats per minute, which is in the normal range for an adult. In this case, we tested when the user is in contact with the stethoscope and when it has been removed and the algorithm is not able to detect a heartbeat. As it can be seen, the output when the user is in contact with the device is 60 beats per minute, but when it has been removed, it should immediately go to 0 beats per minute, but as of now, it has some delay. We also tested when the heart rate is accelerated. In this case, the output is 120 beats per minute initially, and the next time it does give a smaller value, and this could be because it missed a peak that should have been detected. This is something we need to keep on optimizing since we need to have a more reliable output.
Here shows our respiratory rate and body temperature monitoring features in action. This example is on an adult human breathing at a normal rate. The respiratory rate and temperature are printed to the screen every 10 seconds. As you can see, my rate was 15, 23, and 22 breaths per minute for this test. The second example shows what happens when a person is breathing at a normal rate and then stops breathing. I make sure to simulate this by covering my hand in front of my nose so no change in temperature is detected. When no breath is found, an alert is printed to the screen.